Hi guys, I want to talk a little bit today, go over this Kinetics quiz. Pulled the summary up here, and this is before I've graded some of the manually graded questions, but I wanted to go over to how to do these quizzes. The first question here, this was question 1 right here, was one of those formula questions where it gives you all different values, and you have to figure out what the different answers were. So R here, that's the indication of the variable there. So you all saw different versions of this, and let's just pick a value. Let's say that bracket R. Let's say for the argument, let's take an argument that the disappearance of D was found to be 0.100 molar per second, right? Or molars per minute. I guess I specified that unit over there. So molars per minute. So to answer this question, which is a relative rates question, right? Relative rates. What we're looking for is the rate of disappearance of A. So we're looking at A and D. And the way we write those relationships is we say for reactants, negative 1 over the coefficient, so that's the 3, delta A, delta T, which is the rate of change in A. So the rate of disappearance in A is going to be that negative delta A, delta T term, that whole number. That's going to be equal to, we could write equalities with everything, but we're just going to look at D because it's the only one we need. So it's a product, so it's positive. 1 over the coefficient, well, the coefficient is just 1, delta D, delta T. Now that is the rate of appearance. That term right there is the rate of appearance. That's our number right there. So we can just say then that negative delta A, delta T, I'm just going to multiply both sides by 3 and let the 3's cancel out, and then I have just 1 there, so that can disappear. So it's going to be plus 3 times the delta D delta T rate, which is what did I say, 0.100 molar was my example here, molar per minute. So that's just going to be 0.300 molars per minute. And that is an equal sign, not a negative sign there. Usually we use words like appearance and disappearance so that we're dealing with positive numbers there. Question 2, which asks you about terms to complete your rate law. Well, you need to know, basically you need to know the orders with respect to the reactants. So with respect to WRT, the reactants. And then you need to know the rate constant. Calculate that, and then of course the units that are appropriate for that rate constant, I think, are the things that I'm looking for there. In question 3, I'm told you that we are looking at a reaction here, a generic A plus 2B reaction going to some products. And we look at it at different concentrations. And if we keep A constant and we keep temperature constant, which means that the rate constant is the same, it's found that the rate doubles when the concentration of B doubles. So what's the order with respect to A? So this is what I would call an initial rates problem. And to put it in more concrete terms, what we're saying is that A and B, if and rate here, if A is 1 and B is 1, then the rate maybe is 1. If A is 1 and B is 2, the rate becomes 2. That would be an example of data that are consistent with that, where these 2 experiments, which I'll call Roman numeral 1 and Roman numeral 2, were both done at the same temperature. So what we would say is that, we usually look at the ratios of the rates. So the rate of Roman numeral 2 over the rate of Roman numeral 1 is going to be equal to K times the concentration of A in Roman numeral 1 to the X power times the concentration of B in Roman numeral, oops, these are Roman numeral 2's on the top, at the Y power. And on the bottom I'd have K A Roman numeral 1 to the X power, B Roman numeral 1 to the y power. Now, since the temperature is the same, the rate constants are going to be the same. That cancels out. Since a is the same, a to the x is going to be the same, so we'll cancel that out. So all of those terms right there cancel out. We wind up then saying that rate 2 over rate 1, okay, which we said doubles, so that's going to be 2, is equal to b 2 over b1 concentration to the y, and we're also told that when we doubled that, that's going to be doubled, that 2, b2, whatever it is equal to 2 times b1. So so I have 2 is equal to 2 to the y, and the value of y that makes that correct is that y equals 1. So the order with respect to B in this reaction is 1. And of course, typically those orders for individual reactants are usually 0, 1, or 2. So 3 and 4 are fairly out there. Discriminators there, they're are distractors. They're trying to trick you there. Okay, I haven't graded this one yet. Simply, this is looking at integrated rate laws. And we basically talked about different plots that correspond to first, second, and zeroth order reactions. And the one that corresponds to a first order reaction is the one where you have a natural log of A versus the time. That gives you a straight line, and the slope of that line is negative the rate constant for that. So that's what I'll be looking for there. On number 5 here, you're given an example problem applying integrated rate laws, where you've got an initial concentration and so this is our initial concentration here. We've got our rate constant, and then we've got an elapsed time. So we use this is for the second order, so this is our second order integrated rate equation. And of course, those are conveniently summarized for you on your formula sheet. And we just have to deal with doing this calculation, which is, a little bit tricky because you have to deal with not only scientific notation, you've got to deal with doing reciprocals. So it always helps to kind of have a sense of what's going to happen. Obviously, what's going to happen is that the concentration is going to go down. So when I get an answer here that's a little less, I don't feel too bad about that. I think that's a plausible answer. The reaction, we're never going to go past 0, so I'm not going to get a negative number. So I know that answer has got to be between 0 and 0.1. So I feel pretty good about that answer because it does fall in that area. And generally, when you make mistakes on this, you'll make mistakes that will give you something higher that makes it look like it goes up, or that is a negative number. So detecting the mistakes is a very important skill. Question 6 here. Basically what you're doing is using the units to get the order of the reaction. So you remember, if rate is equal to K, I'll just put A to the X here. Then the units, the rate is always in molars, seconds to the -1, molars per second. And we'll just put K in there. And A is always going to be in unit of molarity to the X. So if we solve for K, K is going to be molars second to -1, that's the rate, over molars to the X. So what we're going to have is molars to the 1 minus X, where X is the order, seconds to the -1. So since that's -1, then X must be 2, right? So if 1 minus X, if X is 1, that's 0, it would just be seconds to the -1. That's first order. If it were a second order, then X would be 2. 1 minus 2 is -1, so that would be molars to the -1, seconds to the -1 is what we got. If we have 0th order, 1 minus 0 is 1, so that's molars to the first, seconds to the minus 1. Those are the characteristic units for rate constants in kinetics. So good quick summary there of a bunch of kinetic calculations. I hope that helps you as you prep up for the forthcoming exam.